Lesson 11.7, Ratios of Areas. On your screen you see a target. That is an archery target, if you're not familiar with that. Back when I was in high school, we had an archery section of our PE class, which meant all 30 students had bows and arrows out in the grass, grassy field. That was a frightening exercise. But anyway, you get different scores depending on where you hit on the target. The yellow bullseye is 9 points. The red area here is 7 points, and 5 points for the blue, 3 points for the black, 1 point for the white, and if you miss it, you get no points and you go hunting for your arrow. Okay, well, we know the best spot to hit is the bullseye. Is it most because it's in the center? Is that why it is worth the most, because it's in the center? The answer to that is no. It's not because it's in the center. It's because it has the least amount of area. Okay, so let's look at our yellow area. Yellow area. That's the bullseye. Okay? Well, it is a circle, pi times radius squared. Now, we're going to call all of these units 1 unit. That's a unit there. That's going to be another unit. We'll call this 2 units. Because we can see those nice concentric circles there. So we're going to call this is radius is 2, so 2 squared is 4. 4 pi units squared is the area of the yellow, the bullseye. So now let's look at the red one. So here's my red circle, adds 2 more units to this. So now this the large red circle, it has a radius of 4 to find the radius of everything here. So my red area is going to be pi times 4 squared. But then I'm going to have to subtract that yellow out, right? Because I just want the red. So I'm going to have to subtract my 4 pi away from that. That is 16, take away 4, 12 pi units squared. Follow that? Let's do it for blue. See if you can catch on here. Blue area. Well, the blue area is 2 more units. So 2, 4, 6. 6 units makes the entire radius. So it's going to be 6 squared is 36 pi. And then I'm going to subtract all of what is bounded by the red circle. What was that? Well, that was this 4 squared pi, or 16 pi. We subtract those, and we get 20 pi. Well, we can continue to do this, so on and so forth. Do it for the black, do it for the white. Here's the point that I want to make. Let's look at ratios of these areas. Okay? If I look at the ratio of yellow, which is the bullseye, the most the highest awarded area to hit, and I do the ratio of yellow to let's do red. We can just look at the ratio of the areas. That would be 4 pi to 12 pi. Let's keep my units on there. It's good unit analysis. Good unit analysis here. This is units squared. Could be inches squared, feet squared, whatever. Units squared. Now when I do this, I see that my pi's cancel. I also see that my units squared cancel, and then I reduce my fraction to 1/3. There are no units on this ratio. No units whatsoever. It's not in inches squared, it's not in inches, it is just a fraction that tells us the relative sizes of the yellow area and the red area. And you can see here that there's 3 times more red area than yellow area. 3 times more. So if I'm randomly shooting at this and I have no skill whatsoever, I should hit the red target 3 times as likely as hitting the yellow. And that's why it's not as much of a point value. Okay. Well, we can do this for blue. We could do red area to blue area, for example. Well, what does that give me? Red to blue is 12 pi units squared again to 20 pi. That reduces, cross out your pi's, that reduces to 12 over 20. 12 over 20 reduces to what? 6/10, 3/5, which is equal to 0.6. Okay, so this is, let's write these as a decimal. That's 0.33 repeating. Another kind of interesting note is that as I move outward on the target, this ratio becomes larger. There's a larger disparity between the yellow area and the red area as there is the red area and the blue area, which is 60%. So you can think about it as a percent. This was 33%. The yellow is 33% of the red, and the red is 60% of the blue. Okay. All right. So let's move on. I'm sure as you looked at the target, you probably were thinking, boy, I would like to do this right now. Better not. Probably have that posted in your room, don't you? All right. Let's move forward. I'm going to look at an example here. Okay. I've got a triangle, and this triangle has got, looking at two triangles, the yellow triangle and the red triangle. Okay. All right, let's look at our measurements. If I look at my area of, this is my BDA, that's the yellow, and this is the area of the red, I can find its ratio, and its ratio is given there, 0.96. Okay, so it's 0.96. Now what does that mean? That means if I make it exactly 1, what does that mean about the yellow area, which is on top, and the red area? It means that they're the same, right? The same value on top as on bottom, so those areas are the same. As I adjust this, now notice that my ratio has gone down. Why has it gone down? Well, because my yellow area has decreased and my red area has increased. So I've got a larger number down on bottom than I had on top. So small top, large bottom gives a small ratio. Okay, now think about it always practically as well. That means that if I took this red triangle, 24% of it is the same as the yellow. You can think about it like that. Okay. Well, let's swing it around the other way. Watch it. Watch that ratio grow. Now that ratio is growing. Can be very large. Now I've got a large number on top. Okay. So large on top, small on bottom, makes for a large ratio. Now we understand that mathematically. Let's think about that with the ratio. What that is saying is, since yellow is on top, how many reds go into the yellow? Well, in this case, 3.78 reds will go in to make that yellow area. Okay, think about it like that as well. Okay, so try to get your mind around what the ratios are saying to us. All right, now let's take a look at this problem here. All right, so in the diagram, AB is going to be 5. So we're going to make AB 5 and BC 2. Doesn't look like it's 2. I'll adjust that. Find the ratio of the areas. So looks like that might be more like what it is. Find the ratio of the areas. Now it would appear that we don't have enough information. I mean, after all, how do I find the areas of these things? But what's clever about this sketch? The clever thing about this sketch is this height is the same for both triangles. So let's do the red area. Red area, since it's a triangle, is 1/2 the base. What's the base? Base times height. The base is 2 units and the height is h. I don't know what the height is, but we'll call it h. Yellow area. Yellow area is also triangle. 1/2 base times height. Its base is 5. And we don't know its height, but the heights are the same. So we don't always have to know exactly what the area is to solve these problems. And you can imagine on your homework, you're going to have some of that. So I want to find the area of ABD. ABD is yellow to red. So yellow to red is going to be 1/2 times 5 times the height divided by 1/2 times 2 times the height. Heights cancel because they are the same value. 1/2 over 1/2 cancel. They are the same value. I'm crossing out like factors. I'm left with 5 halves as my ratio of areas. Okay, so that one works kind of slick. The example, the concept we're getting in this example is I don't always have to know what the areas are exactly to find the ratio of the areas. Let's move on. Number 3. So here I've given that AB is parallel to DC. Let's pencil that in. AB parallel with DC. Oh, when I see that sketch and that given, I should immediately realize that I've got similar triangles here. So I've got similar triangles. All right, what is the similarity ratio? So let's write that. I've got ABE, triangle ABE, similar to triangle CDE. CDE, okay? That's what I've got there. Now, the question that we want to find is what is the ratio of the perimeters? Got to mention the given is also that is 5 and DC is 3. Now, this question is really a chapter, whenever that was, 9 question. We've done that already. You should already realize, we all should remember that perimeter, the ratio of the perimeter is the same as the ratio of the similarity ratio. So remember how we found that? We took AB over CD, which was equal to BE over DE, which is equal to AE over CE. And since I knew what BA is and CD, that is my ratio of similarity, which is 5/3. So my ratio of similarity is 5/3. So therefore my perimeter, it is also a one-dimensional distance. So the ratio of my perimeters is 5:3. Done with that. Okay, let me make this comment though. Ratio, remember the ratio of perimeter of two similar figures is equal to the similarity ratio. Okay, so that's old news. Now let's find the ratio of the areas. Is the ratio of the areas going to be 5/3 as well? Now that's a quandary. Is the ratio of areas going to be 5/3 as well? All right. In order to think through this problem, okay, I want to remind you what the difference between one dimensions and two-dimensional characteristics. Perimeter is one-dimensional, all right, and this is one-dimensional. That's one-dimensional. area is two-dimensional. Okay? So that's a little hint that it's not going to come out to be 5/3, but it should come out to be nice. And what I mean by nice is there should be a rule for it. So let's investigate that rule. Okay? So what we're going to do here is we're going to set these. We're going to make the ratio of areas. So I'm going to take this blue triangle right here, ABE. So area of triangle ABE, and we're going to compare that to the area of CDE, area of triangle CDE. All right. Well, how do I write the area there? Well, since we know two side lengths, we're going to call this the base. And this right here, this is not a right triangle. It looks like it's pretty close, but here's my height. There's my height here, h. So it's going to be 1/2 times 5, the base, times height 1. I'm going to call it height 1. The next one is 1/2. The base is 3, so this one is base is 3. Height 2. Okay. All right, now let's consider this. My 1/2s are going to cancel. And what is the ratio of H1 to H2? What is that ratio? If these are similar and the ratio of similarity is 5:3. What is the ratio of height 1 to height 2? That's 5/3 as well. That should be 5/3 as well. So I've got 5/3 times 5/3, and my 1/2's canceled. That's 25/9. My ratio of areas is 25/9 because the ratio of similarity was 5/3. What did I do with the 5 to get to 25? Squared it. What did I do with the 3 to get to 9? I squared it. Here's the lesson. Area is two-dimensional. Perimeter is one-dimensional. One-dimensional. So if I'm going to compare one dimensions with two dimensions, I need to think about squaring. Squaring things. Okay? So let's put that into words here. Okay? Put that into words in the next slide. Two figures are similar, so that's the given. If two figures are similar, then the ratio of their areas equals the square of the ratio of corresponding one-dimensional parts. Oh my, what's that mean? So both of these triangles are similar here. You see, both of these triangles are similar. If I know this base 1, base 2, that is a one-dimensional distance, okay? One-dimensional measurement. So therefore, the ratio of the areas of triangle 1 to triangle 2 is equal to the base B1 squared over B2 squared. That's what that theorem says. Again, I have to have similar shapes. Let's take a look at the second one here. I've got circles. circles are similar. Every circle is similar. Okay? So suppose the circumference of this circle, we'll call it circumference 1. The circumference of this circle, we'll call it circumference 2. Are those one-dimensional parts? Yes. So you can think the ratio of similarity is going to be C1 over C2, but the ratio of areas is going to be C1 squared over C2 squared. Look at the next one. This diagonal right here, we'll call it diagonal 1, corresponds with that diagonal 2 of those similar figures. Those are similar figures, okay? They're similar. We have to have similar figures. In order to use this, they must be similar, okay? Be sure you remember that. This is given. They have to be similar. So, what is the ratio of areas? Area 1 to area of figure 2 is equal to the diagonal 1 squared over diagonal 2 squared. It's that simple. Let's look at an example. If ratio of the areas of two similar parallelograms is 49 to 121, find the ratio of their bases. Let's sketch this out. What are we talking about? We're talking about two similar parallelograms. So I've got, here's a parallelogram, and these are supposed to be similar, okay? We were given that they were similar. And their ratio, we are given the ratio of their areas. The ratio of the areas is 49 to 121. So this was 49 to 121. That doesn't mean that the area is 49 units, and that one's 121 units squared. It doesn't mean that. It means that the ratio is 49 to 121. Now we want to find the ratio of their bases. So now I've got the ratio of their areas. So what am I going to do? Square root both sides, right? So I have 7 over 11. The ratio of their bases is 7. 7x to some 11x is the ratio. Okay? Alright, so because if I have the bases, if I knew this base 1 to base 2 is equal to the square of those, by the definition from the last slide, and we knew that was 49 121s. So, how do I figure out what base 1 is? But I square root 49 and I square root 121. Alright. Not easy. Take a little practice, but we'll get it. Alright. Something quirky going on here. I've got AM is a median of triangle ABC. Should say ADC, I guess, right? Change that to ABC. Alright, no, that should be D. Sorry. That needs to be D, and I need to change this. There we go. Alright, so AM, this is a median. What does a median mean? It means divides the base in congruent parts. So these are congruent, right? It's on the midpoint. Alright. What is the ratio of yellow to red? I want you to just look at these measurements. Here's the measurements. AMC, that's yellow area. This is red area. Notice that those areas are the same. Let me play with this triangle. What do you notice? Those areas are always the same. Strange. That means the ratio is going to be 1. Red to yellow is 1 to 1. Doesn't matter for what triangle. What's the constraint? That's got to be a median right there. It's got to be a median. Why? Why is that the case? Okay, I will leave that for you for extra credit. Prove that when I have a triangle, the median divides the triangle into equal area. So here it is. A median divides a triangle into equal area regions. Prove it for extra. Alright, and with that we will conclude tonight. See you in the morning.